So last day, I'll try to survey the semester. I know from experience that time goes by pretty fast, so I'll try to be careful. Just last things to remind you, do complete the course evaluation on Colab. You don't have to go into the course itself. You just log in and you'll see the opportunity to do course evaluations. And it's due by, I believe, tomorrow evening. It's run by the university, not me. So if you miss the deadline, you miss the deadline. It's over. But if you do it, I drop the lowest problem set score. All right? So even if it's a 0. Anyway, so incentive. The final exam, last thing in the course, is a week from today, 9 o'clock in the morning, 60 multiple choice questions, same kind of things you've seen all along. I encourage you to take the old exams. Be aware, of course, that some of the topics will have, long enough in the past, either don't do them anymore or they've changed. So not all the questions will be relevant. Any questions about exam stuff? All right. So rather than differentiate the first 6 topics, I know I bogged down in them if I go skating and then falling balls and stuff. They were primarily contexts in which to sort of introduce the language of physics, the physical quantities that matter a lot for us, like acceleration in particular, mass, and what's that? What's a force? I'll remind you that probably contrary to intuition, forces don't cause things to move. They cause things to accelerate. So objects move because they were moving. That's the concept of inertia. They keep doing what they're doing until you bother them. So to keep something moving, you don't have to push it. You just have to not stop it. So remember that. I introduced a couple of forces. Gravity, which is a force that acts on everything here near the surface of the Earth. And amazingly, it exerts a force on objects that is proportional to their mass. Even though gravity, or an object's weight, which is the force of gravity on that object, and the object's mass, they're different quantities. The weight is how hard the Earth pulls down, and mass is how hard it is to make something accelerate. And the fact that they're proportional to one another is actually kind of a remarkable thing. It is the case. It leads to interesting effects like all things fall together. That is, you drop a big massive bowling ball, say, in a little marble. Yeah, they have different weights, and that should affect their accelerations. But they also have different masses, and that should affect their accelerations. And they cancel. So the bowling ball and the marble accelerate downward at the same rate. Okay? And you're welcome to ask me questions if there are things that I should come back to and discuss or you're wondering about. In the context of ramps, I started to introduce the first of several conserved quantities of nature that turn out to be pretty important or useful in just sort of figuring out how your world works. And this one was energy. And energy followed us the whole semester. It's sort of a basic tool for looking at almost everything we ever looked at afterwards. It's defined as the capacity to do work, and work is the mechanical means for transferring energy. It's a little circular, but it is a conserved quantity that things carry with them. And so if you look at something, you can, in principle, figure out how much energy it's carrying with it. It can have energy in its motion, that's kinetic energy, and it can have potential energy, which is energy stored in the forces. And because it's a conserved quantity, an object can't change its energy without transferring it one way or the other. And it transfers it by doing work. You're pushing on something for a distance. So for me to transfer energy to, this gadget, I have to push on it, and it has to move a distance in the direction of my push. If it moves a distance opposite my push, I take energy out of it. I do negative work on it. Okay, we saw work show up again in things like a transformer, where there's an electric field in a transformer that does work on electric charges. It pushes them as they move a distance in the direction of the push. It does work on them, transfers energy to them. All right. One of the features or behaviors that showed up in ramps was the idea that you can do the same work on an object with different forces for different distances, and that's often useful in everyday life, where you're trying to do something that requires, by itself, an enormous force that you just can't summon. You can't lift a grand piano straight up a ladder. It's not going to happen. But you can do the same work of lifting the piano from the ground floor to the 5th floor. Don't use a ladder. Use a ramp or something equivalent to a ramp, in which case you can do the work of raising the altitude of the piano, and therefore its gravitational potential energy, using a smaller force, one that you can manage, but for a longer distance. And whether it's a ramp or it's some sort of pulley system, a topic I used to do, which is, it's still up there on the catwalk, the pulleys I used to play with. It doesn't matter. The concept's still the same. You can do, if you have to do the work, a certain amount of work to get an object from this situation to that more energetic situation, figure out a way that you can deal with. You may have to use less force for more distance or more force for less distance. It all works out. All right? The other two conserved quantities that showed up soon thereafter were momentum and angular momentum. I didn't dwell on these as much later in the course as I guess I could have in some ways. But they're there too. They're following along when you're trying to make electric current flow through a wire or something like that, and you want to keep the electric charges moving at a steady pace. That means you want to have them carry the same momentum with them. It's a conserved quantity after all. So if nobody transfers momentum in or out of the charges, they'll keep doing what they were doing. They'll keep moving with constant momentum. In a real wire, the wire pushes backwards on the charges, taking out their forward momentum. So you have to push forward to restore it. And what do you push forward with? A force for time, an electric field. Okay, so the momentum was there. I'll remind you, it's transferred by exerting a force for time, which I alluded to a moment ago. So the movement isn't so important. You can transfer momentum to things that don't move. It's not a problem there. Often you care about the relationship between force and time. I mean, in everyday life, you routinely try not to transfer momentum quickly. It hurts. It involves big forces. So what do? You transfer momentum slowly. Land on when you do the high jump, you want to land in a soft mat that takes your momentum out slowly. You don't want to land on a concrete slab. It takes your momentum out too fast and it doesn't feel good. Angular momentum was another conserved quantity that's associated with rotation. An object that is turning carries with it this conserved quantity, angular momentum, and if it doesn't exchange it with something, it can't stop turning. It can change how fast it's turning because if it can change its shape. There's a funny, the skater trick problem in there where if they can change rotational mass, which is reflects the shape of the object, they can change an object that can change its rotational mass can change its angular velocity without changing its angular momentum. The product of the two is the angular momentum. So you can do weird things like the skater trick, shrink your rotational mass and increase your angular velocity. That works out okay, even if you have no exchange of angular momentum. So with that, I think I'll probably leave the first 6 topics. Anything else that you care to hear about in those guys? All right. So then I went off into electric charge, the world of that, and in particular, static electricity. And we saw that there's this other conserved quantity in nature known as electric charge. Again, you can't create it or destroy it. If you got it, you got it. You have to move it around. It's moved by exchanging charge. It's nothing special there. And it turns out that objects with like charges repel, objects with opposite charges attract. The like and opposite is sort of a shorthand way of referring to the fact that some objects have a positive amount of charge. We say they're positively charged. And some of them have a negative amount of charge, negative amount of that conserved quantity. And we call that a negative charge. There's a subtle difference between a negative amount of charge and negative charge, but it's not very complicated. And opposite charges attract, like charges repel, and the forces between them get weaker with distance. And specifically, they go as 1 over the square of the distance, 1 divided by the square of the distance, a feature that shows up in physics or in our universe more than once. The forces of gravity has the same sort of situation with it. It decreases with distance as 1 over the square of the distance. All right. I then, after talking about how charges interact with each other, talked about the idea of voltage, which measures the amount of energy, specifically the electrostatic potential energy, that charge has at a particular location in space. So voltage is a feature, I should say, is a physical quantity associated with each point in space. Each point in space has a voltage. And that means that if you found a certain amount of charge there, and the classic choice of how much charge would be a coulomb, 1 unit charge. If that point in space has a voltage of 100 volts, that means that if you were to take 1 coulomb of charge at that location would have 100 joules of electrostatic potential energy, which it could release in principle by going to some place that has the voltage of 0. So voltage measures how much energy positive charge has at that location. And it's a per charge measurement, so that you divide out by how much charge you have in mind. So it's the energy, energy per charge. Accumulations of positive charge tend to have large positive voltages. They are places that positive charge wants to leave and will release energy in leaving. So if the positive charge at that location has a lot of energy per charge, as in a big voltage, positive voltage. Negative voltage is negative voltage, I can introduce that without introducing negative charge. Negative voltages are destinations to which positive charge loves to go. They're typically accumulations of negative charge. So they're very appealing to positive charge. It wants to go there. It will release energy in going there. So negative voltages, charge tends to go from positive voltage to negative voltage, or at least to lower voltage. And that shows up everywhere in electrical gadgetry. Charge is moving from positive voltage to negative voltage, or at least to lower voltage. All right? Negative charge has the weird characteristic that does everything backwards as compared to positive charge. Negative charge likes to go from negative voltage to positive voltage, or at least to higher voltage. It goes backwards. That's good enough. Any questions about electric charge stuff and voltage? Looking at electrostatic copiers, then I came across the idea that if you have different voltages in a system, say positive voltage over here, negative voltage over there, then there is a voltage gradient between them. That is, the voltage doesn't go. I mean, there are voltages in between, in the air, in the nothing in between. There is a voltage. It measures how much energy a charge would have, a positive charge would have per charge there. So the voltage doesn't abruptly go from one to the other. It swoops from, say, positive voltage to negative voltage. And that gradient in voltage, where you get a continuous change in the voltage with location, that is an electric field. An electric field points toward lower voltage. So what that means is that if you have two big sheets here, to make it very simple and symmetric, two big sheets of metal, one at positive 1,000 volts, one at negative 1,000 volts, the voltage will actually swoop very uniformly between them. And the details of why it's uniform is like beyond this class. But that means that there is an electric field between those two plates, and it's steady and it points toward the right nicely, from the high voltage to the low voltage. All right? There's a question that I asked several times, and I scored incorrectly the second midterm. One where there's only a pin facing a sheet. Remember that question, if you do? And that question, it's not two sheets, one at positive 1,000 volts, one at negative 1,000 volts. It's a pin and a sheet. And at the midpoint between the two, the voltage is not 0. Because, as it would be if these were two sheets. But because it's a pin, if you were a bug sitting there at the middle, looking to the left and looking to the right, you would see the sheet. It looks big. It dominates your field of view over here. If you look to the right, you look at the pin, you say, I can't even see it. It's a tiny little thing. Yes, it has let's say the pin was positive voltage. I forget what the question had it as. Say it's positive, this guy's negative. You look at that positively charged pin, positive voltage pin, it's so small. Yes, it's plus 1,000 volts, but it doesn't have much effect on you or the location. Charge at that location doesn't care about this tiny little pin with 1,000 volts on it. The voltage here at the center between the two is dominated by the sheet and is essentially, the sheet's a minus 1,000, this guy's minus 980. It's barely different. It isn't until you get very close, you the bug, get very close to the pin and you begin to see it as large in your field of view as the sheet. And that's where the voltage does all its changing. Consequently, that's where the electric field is strongest, because the electric field is the gradient minus, the gradient in the voltage. And so right near that pin, there's a tremendous electric field as the voltage swoops toward the pin's voltage. And why did this all matter? Where does it show up in real life? Well, it shows up in your electrostatic copier as that electric field is so strong there that it can do neat things like put charge onto the passing air molecules. So that's how the electrostatic copier or your laser printer, that's how they manage to put electric charge on the stuff that's used finally to do the printing. It's also useful in things like your lightning rods. How do the lightning rods above your house, if you have them, or they're certainly around, even if you don't have any, what are those doing? Well, they're creating strong electric fields near them because they're sharp guys, little sharp guys at one voltage. As a cloud goes over at another voltage, all the voltage change occurs near the points of the lightning rods. Big voltage change, that's a big voltage gradient, strong electric field, charge gets shot off into the air and it discharges the cloud. So that's the point of lightning rods, is try to prevent lightning altogether. Okay, so the point of this was just to remind you that what voltage is and the variations in voltage across space, across position, are associated with electric fields. They actually are electric fields. I then talked about how the simplest of electric circuits work, essentially a flashlight or anything related to equivalent to a flashlight. It's just a source of electric power, such as batteries, and a consumer of electric power, such as a light bulb, and conduits for electric current, like wires, and a switch. And the idea here was that in a source of electric power, charge enters at low voltage, that is low energy per charge, and energy is given to the charge. So it leaves at high energy per charge, high voltage. Keep harping on the energy per charge being voltage. Hopefully it starts to sort of settle in that that's what you're measuring. And so batteries do this. They manage to take in charge at low voltage and pump it chemically to high voltage. A process that it gives the charge more energy, and therefore the energy's got to come from somewhere. It comes from the chemicals in the battery being consumed. So that's why batteries run out. And typically, the physically larger the battery is, unless you're being cheated, the physically larger the battery is, the more chemical potential energy it has stored, and so the more charge it can move over the life of its capacity, until it's a dead battery and you've got to do something about it. On the other hand, the consumer electric power, let me just remind you that because charge enters the battery at low voltage and leaves at high voltage, we describe that as a voltage rise. The current electric charge experiences a rise in voltage in going through a power source, like a battery. The consumer of electric power, it's the opposite. The charge enters at high voltage and leaves at low voltage, having given up energy per charge, given up voltage. So a consumer of electric power like a light bulb is created with the idea that it's supposed to consume a lot of the energy per charge that was available, use that energy to make light, if it's a light bulb, or whatever it's supposed to be doing, and then send the charge back to pick up more energy. It doesn't want to accumulate the charge because that charge, as it accumulates, begins to repel subsequent charge. So you can't make a system that delivers power from a source to a destination or consumer that has only one wire. You need two wires. Just to harp on that one too. The whole reason for a circuit is it's very difficult to convey over a lot of electric energy from the battery, say, to the light bulb if you only have one wire, because you only get to deliver the charge once. You can't get it back. So what do? Have a second wire that returns the charge at low energy per charge. In other words, low voltage. Go get more energy, come back at high voltage, and so on. All right? I talked about how the wires themselves are consumers of electric power. That's not great. You would love to have that not be the case, but it turns out that charge will not coast through ordinary metals. Yeah, it's got inertia and all that stuff. And in principle, if the wire just didn't mess with the charge, it would be great. The charge would enter at a certain voltage. It would leave at the same voltage, no problem. All the energy would make it to the far end. That doesn't happen. Metals consume some amount of energy as the charge goes by. And the more charge you try to shove through a wire every second, which is to say more current you try to drive through the wire, the harder you have to push to make up for the energy loss. So this is the origins of what was called Ohm's Law. The idea that if you look at a wire or anything like a wire, which generically they're called ohmic devices because they obey Ohm's Law. Wires do this. If you look at a wire, the current going through it experiences a drop in voltage. It enters at higher voltage, leaves at lower voltage. The current is lost, is wasted power heating up the wire, and the amount of current that went through the wire, I don't want to say, the amount of voltage you have to apply to the wire. I'm thinking through Ohm's Law. You can smell the wood burning probably. The voltage drop that occurs in the wire as you try to shove the current through it is going to be proportional to how much current you want to have go through it. And it's also proportional to how much this wire intrinsically resists the flow of current, what's called its resistance. So if you take a wire that's got very low resistance, really good conductor of electricity, you don't have to push very hard to get a pretty big current going through it. On the other hand, if you take a wire that's a terrible conductor of electricity, the heating element in a toaster is designed to be a crummy conductor of electricity. Now you have to push quite hard, big voltage drop across it to shove even a modest current through. And the consequence is that a lot of energy is taken from every charge, the wire gets nice and hot, and that's that. All right? So that's the story of simple circuits. I'll remind you just because you want to remember this just for your own use. Short circuits, the real meaning of a short circuit as opposed to just sort of people using it, they short-circuited me or whatever it is. No. The real meaning of a short circuit is when you have some conducting path that bypasses what is supposed to be the consumer of electric power, like the light bulb. So if you went up into these light fixtures overhead and you added a wire that just took power coming from the power company, current coming from the power company, and just sent it right back to the power company, skipping the light, this would be a bad thing. It would sparks and overheating, and it would probably blow the circuit breakers to rescue us. So avoid short circuits. You do not want to add wiring that bypasses what's supposed to be the consumer of electric power. All right? Magnetism. So then we turn to seemingly separate worlds, like the world of bar magnets pushing on each other and stuff. And it turns out, well, there's another conserved quantity called magnetic pole. And you can have a positive amount of it or a negative amount of it, or none. And we just, having used the word positive and negative already to describe electric charge, it makes sense to pick a new word. So they use north and south to describe it. North is a positive amount of pole, and south is a negative amount of pole. They have, the origins of those names have to do with navigation in the Earth. The Earth happens to be a big bar magnet, effectively. So it's a conserved quantity. What's different? And like poles repel and opposite poles attract, and the forces get weaker with distance, like 1/r². Wow, it looks just like electricity, electric charge, except for one detail, and that is no one's ever found an isolated portion of pole. No object exists that we've ever seen that has a net pole that's not 0. So if you look around, you find an object that's got, it's got a positive pole over here, that is north pole over here, it's going to have the same amount of south pole somewhere else. It just always happens. Disappointment city for the scientists looking for loose pole. It just hasn't been found yet. That's okay. I mean, you can still have magnetic influences. You get the attraction, you get the repulsion at the same time. They may have different strengths, but you can't get just pure repulsion or pure attraction. You're dealing with something more complicated. The details, well, magnetic materials. Where does pole show up from? I should say, charge just comes along with some of the subatomic particles. No one's ever found an electron that wasn't negatively charged, that wasn't carrying one fundamental unit of negative charge. And nobody's ever found a proton that doesn't carry one positive fundamental unit of electric charge. And there are some other charged particles in nature, but they're exotic. So those are the main ones that matter. Magnetic pole shows up on subatomic particles too, but always in pairing. It always shows up with net pole 0. So things like an electron has a north pole and a south pole, but the electron's overall pole is 0. Net pole is 0. When you start building materials, the stuff of everyday life, it's got zillions of particles and stuff in it, and in most cases, the magnetic pole cancels out to 0 everywhere. You find no obvious magnetic poles anywhere. So in a person, we have almost nothing magnetic going on in us. Most materials are like that. There are a few oddballs like iron, and iron's sophisticated older sibling, steel. Those actually do have actual magnetic character intrinsic to them from how they assembled out of electrons and other particles. But usually it's not noticeable because although these materials are intrinsically magnetic, it's masked by disorder, that they're like a whole box full of bar magnets just scrambled all randomly, and therefore they all cancel. And so you get nothing. The little bar magnets are like what are called domains, the magnetic domains, if you recall. So magnetic domains in a piece of iron or steel coming right out of the fabricator, the domains are all, I wouldn't say random, but they're oriented so that they cancel one another's magnetism. You don't see any magnetism. To see the magnetism, you have to line up the domains. You have to force them to change size and shape until you end up with all of them agreeing that we're going to have our north pole that way and our south pole that way. And you can do this with another magnet. You can force them all to evolve so that if you bring up a north pole towards the bottom of the material is going to evolve so that all of its domains have their south pole near that north pole. They like this. This releases energy. And so the material will magnetize. And the big question then is, to what extent did it magnetize, and how easy is it for it to forget its magnetization? And if you recall, soft magnetic materials, like pure iron, they're easy to magnetize and they're easy to unmagnetize, demagnetize. They forget the magnetization almost immediately after you take away whatever magnetized them. That's in contrast to hard magnetic materials, which are difficult to magnetize and consequently difficult to demagnetize. I should say that easy to magnetize is accompanied naturally with easy to demagnetize. You don't get, they're the same idea. If it's easy, it's easy to change the magnetization. So some materials are easy to change in any way you like, magnetize or demagnetize. Some materials are hard to change either way, magnetize or demagnetize. The easy to magnetize materials are used in things like transformer cores, which get magnetized back and forth all the time, or the doorbell components that ring the door. You magnetize them and they go ding, and they demagnetize them and they go dong. Remember, I played around with that. So that's where you want easy to magnetize and demagnetize materials, soft. On the other hand, if you want something that remembers its magnetization, like a permanent magnet or the magnetic strip on your credit card, then you want a material that is hard to magnetize and also hard to demagnetize. So it's magnetized once, it stays that way for a very long time until somebody messes with it. All right? So that was the world of magnetism. Up to a point, then we encountered the fact that, well, you can also make magnetic fields, the part of what lives around the magnetic poles is a magnetic field, and you can make magnetic fields with electric currents. And that was it was a surprise to the scientists who observed it first, and it's kind of, where did this come from? Because that brings together the world of electricity. An electric current is just moving charge. Nobody said that would be magnetic. And suddenly it has the characteristics of a magnetic field. They're connected. So this is the first connection between electricity and magnetism. Electric currents, which is the same as moving electric charges, are magnetic. They have a magnetic field. Subsequently, we encountered a couple of other ways in which electricity and magnetism are connected. So moving or changing electric stuff is magnetic, and moving or changing magnetic stuff is electric. They go back and forth. It's very symmetric, except that there are no isolated magnetic poles around, so you can't make a current. A magnetic current is hard to make. An electric current's easy. The free electric charge is no problem. It's hard to make a magnetic current. But anyway, they're very symmetric. So we saw that moving charge is magnetic, and it's useful in things like creating an electromagnet. Magnet you can turn on with electricity. We then went into to talk about transformers. I started talking, my next topic then was transformers, and looking at the idea that, well, if you want to deliver electric power long distances, and you have to deal, and it seems, this is a sort of change in story. If you want to deliver electric power long distance from a power plant off, I don't know, Niagara Falls, which is actually one of the issues early on, you want to deliver that power to a city far away like New York City, well, you're going to lose a lot of the electric power in the wires because wires don't carry current for free. So what are you going to do? Well, you want to minimize the amount of current in those wires, because it turns out that the power wasted in a wire is proportional to the square of the current passing through it. For reason, I'll leave that reason in the past. So minimize the current. How do you deliver a lot of power while minimizing the current? Well, use high voltages. Have two wires that, instead of being separated by 10 volts and carrying huge currents in order to deliver decent power, separate them by 1,000,000 volts. And you can use dinky currents then and still deliver a lot of power. Because the power you're delivering is still going to be the product of the current you deliver times the voltage difference available to that current. How much energy per charge the current could drop off. So crank down the current to save energy, and crank up the voltage to make sure you keep delivering power at the pace you like. So that means to go from Niagara Falls to New York City, you want very high voltage transmission lines, which you got to protect people from because they're dangerous. High voltages tend to push charge off into things and no fun. You can't deliver power to a household at 1,000,000 volts. That is, you don't want a 1,000,000 volt flashlight. Too dangerous. So what do? You have to move power from circuit to circuit. You want to move power from a circuit that has a high voltage between its two arms, the delivery arm and the return arm. You want a big voltage there so you can use small currents. But you want to move the power from this long-distance transmission system to a household delivery system where the voltage difference between the wire through which you deliver current to the house and the wire through which you receive the current back from the house, you want to make that voltage difference small. How do you move power from between these two circuits? And they're truly separate circuits. If you watch the charges going around the long-distance transmission lines, they never leave those lines. They start at some facility in maybe Niagara Falls, and They end at some substation, maybe outside New York City, but they keep going around that circuit. They never go to your house. It's a separate circuit that goes through your house. The two circuits come close to each other only in a transformer, and they don't touch, and they don't exchange charge. It's just the power goes from one to the other, and the power goes by way of electromagnetic influences. And for that to happen, the currents have to be dynamic. They have to change with time, so that they create magnetic fields that change with time, and magnetic fields that change with time create electric fields. And it's that interplay between magnetic fields and electric fields that allows power to move from circuit to circuit. All right? The details of that, you can go back and look at the notes or the book. Is that okay? It may be that in your lifetime, the power grid will evolve significantly, but for the past 130, 40 years, it's been this AC power system. Very, it's an odd situation where the individual pairs of wires, like the outlet wires, they do not have a fixed voltage difference between them. They're not like a battery. They have a voltage difference that fluctuates back and forth. So that there are moments in time where one wire is the high voltage and the other is the low voltage, and very short time later, it will be reversed. So the current literally alternates its direction of travel through all the circuitry. And that allows the power to move through the transformers. All right. I then went on and talked about electromagnetic waves, the first of which was radio waves. And the idea here was that, well, if you have a charge that's motionless, it just creates an electric field around it, which I glossed over earlier today, but we're okay with that, I hope. It's just got an electric field that just lives around it. If you have a current of charge, so you've got a train of charges heading off to the right, for example, now it has both an electric field around it because it's an electric charge. It also has a magnetic field around it because it's moving charge. Okay? But they're sitting there, the electric field, the magnetic field is steady. If you take this charge and you make it accelerate, so don't have the steady train, have a train that keeps going backwards and forwards. Now you've got the change that you need to do something special, to launch an electromagnetic wave. And long and short of it is, whenever charge accelerates, it emits electromagnetic waves. So not motionless, not in steady motion, it's when it's in accelerating motion that you get an electromagnetic wave coming off. And the electromagnetic wave that leaves and propagates and can go on forever across the universe, it consists of only two things, an electric field and a magnetic field. And because each of those is changing with time at any given location in space, it creates the other. So a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and the two are creating one another. And I keep sort of meaning to get the famous Escher painting of the hand drawing itself. Or maybe it's two hands drawing themselves. Anyway, ideally it would be two hands drawing themselves. And so that's what's going on here. The electromagnetic field are creating one another, and they're an independent ripple that travels across through totally empty space at the famous speed of light. And what else? No charge. They don't need charge or magnetic pole near them. They're perfectly happy as a stable ripple. It heads off. To launch one, you need electric charge or magnetic pole. To receive one, you need electric charge or magnetic pole. But en route, just the fields. And they carry energy, which the electromagnetic wave carries energy in its fields, because it turns out electric and magnetic fields both contain energy. All right? Radio waves cover a certain portion of what's called the electromagnetic spectrum, the low frequency end. Low frequency, long wavelength end of the electromagnetic spectrum. If you start working up towards higher frequency, shorter wavelength, you get to microwaves. And that was what you use to cook food in a microwave oven. And it's part of Wi-Fi, your cell phone communication. Those are all microwave. If you go higher still in frequency, you get to light. Initially, you get to infrared light, which we can't see, but then you get into visible light. Starting at the red end of the spectrum, that's the lowest frequency, longest wavelength of the visible spectrum. And you work your way towards blue and violet, which are the highest frequency, shortest wavelength, and then on into ultraviolet, X-rays, and gamma rays. Is that okay? With light, you can start to look at some of the interesting things that happen to waves as they go through stuff. And this is true not just of electromagnetic waves, and certainly not just true of light. It happens to radio waves, microwaves. It happens to water waves, sound waves, all these interesting things like refraction or reflection. Whenever light encounters surfaces where it changes speed, so it's saying going from air where it travels quite fast to going to plastic where it travels much slower, at that interface, the electric field, the magnetic field, the relationship between them changes abruptly, and there is two things happen. One is that there's a partial reflection off that surface, and the other thing is that tends to be refraction. The wave doesn't travel the same direction once it gets inside the surface. The exception is if it hits the surface exactly head-on, perpendicular to the surface, it comes plowing right into the surface, head-on, it goes through and continues head-on. But if it hit at any sort of angle, it will bend. The hand wavy argument that I never used in class was, suppose this is the surface here, this front of this desk, and I'm the wave, and I hit head-on, I keep going head-on. But if I hit at an angle, and the wave actually has some width and extent to it, if I come in at an angle, my hand is already entering, right? And let's let that be plastic and I'm in air. Okay, so my hand is going to slow down, and my arm is going to slow down, and my body is going to slow down, and my other hand, the turning sort of follows naturally, because the parts of my wide wave here are slowing down separately. Can you imagine that I have to turn to go more directly into the material? There's some physics in that. In part, it's also just sort of a way of remembering which way the wave bends. On coming out, it does the reverse. Is it okay? Refraction, reflection, there's this phenomenon known as dispersion, which is the observation that in most materials, light, specifically for light, the speed with which light travels through the material depends on its frequency/wavelength. And the higher the frequency, shorter the wavelength, the slower it travels. Which, in other words, the violet end of the visible spectrum travels more slowly than the red end of the spectrum. And this by itself doesn't have much effect. You never notice it in windows, or rarely notice it in a window. But you do notice it in things that have cut facets on it, like diamonds and other jewelry. You notice it in water droplets for the rainbow. You would certainly notice it in camera lenses if they were dirt cheap, if they didn't work to correct this kind of problem. You get the main way in which this dispersion effect influences life for us is that it means that the colors of white light, of light, say, from the sun, they get separated because of refraction, the refraction effects being dependent on color. The violets bend more than the reds because they experience a stronger refraction as they slow down more or speed up more. All right? What other things about light? Oh, interference effects. This first encounter with interference effects, where if you take a single wave, one like a radio wave, or a single light wave, any of these will work, and you break it into pieces with something, for example, a partial reflection off of a surface, and you have multiple surfaces, you get multiple partial reflections, then when those partial waves, as they're called, these pieces of the original wave coincide on something, their electric and magnetic fields can add, you have to sum them up because they all have their own influence, but if they add up, if they are oriented together, they add constructively, they help each other. If they're oriented opposite one another, they cancel, or at least partly cancel one another, and they create destructive interference. So interference effects are common in the world of waves, where you have the wave broken into pieces and then overlapping. We saw that with soap films. That shows up in microwave ovens where you get uneven cooking because the microwave oven is filled with pieces of the wave that bounce off corners in funny ways and stuff like that. And when they overlap on your food, sometimes they overlap in a way that cooks a particular location very strongly, and sometimes they overlap in a way that doesn't cook well at all. And so you get hot spots and cold spots. And the simplest solution that you've encountered most of your life is to have a carousel turning. So the food moves around. It doesn't sit in one spot getting either overcooked or undercooked. So it blurs out this effect. All right. Move on to creating light. You can create light with a hot surface. You get the particles jiggling around vigorously and therefore accelerating vigorously. They will emit electromagnetic waves. And so that's where the sun's light comes from. It's thermal radiation from the accelerating charges. You can create light more sophisticatedly by using an electric discharge, where you put energy into atoms and you watch the atoms emit light, not because they're hot, but because you've deliberately put energy into them, and they emit light typically that's characteristic of their quantum structure. The orbitals, remember all that stuff with the orbitals and radiative transitions from one group of orbitals to another. You don't have to have the atoms or the system, the gas, hot. Finally, the most sophisticated way to making light was, well, an LED was en route. When you have a light-emitting diode, this was a solid-state device that strategically puts electrons into high energy, now they're called levels rather than orbitals. They're put into conduction levels by the structure of the LED, so they're in a quantum state anyway that has a lot of energy, and they're given the opportunity of shifting into a quantum level in the valence band that has much less energy. And they do that shift. They don't move in space, they move in energy. From high energy to low energy, the wave changes structure in that process, and the missing energy goes out as light. So that's a light-emitting diode. And if the diode is more sophisticated in its physical structure and some of its other properties, it can do things like amplify passing light. So when light is traveling past it, another light wave is coming by that it is capable of emitting, it will glom on and amplify that light. It will duplicate it. And so you'll start with a weak light wave and boost it up into a strong light wave. And that light amplification by stimulated emission of radiation is a laser. So lasers are using systems that can amplify passing light. And to make a laser capable of just producing its own beam of light, you put mirrors around it. You let it see its own reflection. And the light rattling back and forth between the mirrors gets amplified over and over. And if you allow a little bit of the light to escape as a laser beam, you've got a laser pointer or whatever other laser you want to make. This also does point out the quantum nature of light. It's not just a wave, it also has a quanta. It's emitted and absorbed in packets known as photons. And the energy in one of these packets, the photon packet, is proportional to the frequency of the wave. So the high frequency light, like ultraviolet and X-ray and gamma ray, they carry a lot of energy per packet, which is what makes them biohazardous. You don't really want to be exposing yourself for long periods to these high energy packets of light, because they can do chemical damage and all that stuff. I then talked about cameras, the idea that you can use refraction to bend light and form images. Most of the focus was on real images where you actually make a pattern of light that you can put your hand in. You can put film in, you can put a light sensor in for your camera. There are also images that you can't touch, but you can see them anyway. And that's like the virtual image of a magnifying glass. I then talked about how you can channel light through things like fiber optics using a phenomenon known as total internal reflection. That if you take light that's trying to leave a material in which it's traveling slowly to enter a material in which it would travel fast, if you let it hit the surface between the two at a very shallow angle, the bend away from the perpendicular is so severe that the light doesn't get out at all. It remains trapped inside the material in which it travels slow, and it can bounce back and forth repeatedly and travel for miles, which is how fiber optics work. And the last thing I'll say 2 cents on is nuclear weapons. The ones that I talked about, the fission weapons, release the energy stored electrostatic potential energy stored in giant nuclei where you've got too many protons packed very tightly. If you can get them to come apart, they release electrostatic potential energy in just astonishing amounts, and kaboom. How do you do that? Well, the most successful, alas, way of doing this is by way of a chain reaction in which a neutron sneaks up on a giant nucleus. Neutron being a substantial particle with no charge, so it can sneak right up to the nucleus without the nucleus knowing it's coming and crack the nucleus in half. Not all nuclei will crack, but some will. Uranium-235 is an example, and so is plutonium-239. When they crack, they fly apart into pieces, which themselves release more neutrons, which can subsequently cause other nuclei to crack. And when that gets carried away, you get a nuclear explosion. And with that, I think I've at least walked across the whole semester, hopefully of some value